Welcome to Soft Spoken Mysteries, where we explore the incredible achievements and engineering marvels of the ancient world. If you're enjoying these deep dives into history's greatest accomplishments, please hit that like button and subscribe so you never miss an episode. Today's journey takes us to one of the most astonishing engineering triumphs ever achieved, a city that shouldn't exist, built in a place where life itself seemed impossible. In the heart of Jordan's desert, carved directly into rose-coloured sandstone cliffs, stands the ancient city of Petra. You might recognise it from Indiana Jones and the Last Crusade, where Harrison Ford discovered the Holy Grail hidden within its most famous structure, the Treasury. But the real mystery of Petra isn't about fictional relics. It's about something far more impressive. How did an ancient civilization build a thriving metropolis of 20,000 people in one of the harshest deserts on Earth without a single natural water source nearby? The Nabataean people accomplished what modern engineers still study in awe. They created a water system so sophisticated, so precisely calculated, that it predated Western hydraulic science by 2,000 years. And in 2024, archaeologists made a stunning discovery beneath the Treasury itself, revealing secrets that are rewriting what we know about this ancient marvel. This is the story of impossible engineering, of human ingenuity triumphing over nature's harshest challenges, and of knowledge so advanced it seems to defy the timeline of history itself. Let me set the scene for you. Imagine standing in the Psyche, a narrow gorge carved by water over millions of years, its walls rising 200 feet on either side of you. The passage is so narrow in places that you could reach out and touch both walls at once. As you walk this natural corridor, the walls change colour with the light, shifting from deep crimson to soft pink to golden amber. And then, at the end of this winding passage, you see it. Through a gap no wider than a doorway, the Treasury reveals itself. 40 metres tall, carved entirely from the living rock, its Hellenistic columns and intricate facades impossibly preserved for over 2,000 years. But here's what most visitors never see, what makes this achievement truly staggering. Look carefully at the walls of the Psyche as you walk. On the left side, carved into the rock face, runs a covered channel. On the right side, embedded into the cliff, a series of terracotta pipes. Both are bringing water into the city, not carrying it away, bringing it in. From where? From springs 5 miles distant, across some of the most challenging terrain imaginable. The Nabataeans built this 2,000 years ago, without modern surveying equipment, without calculators, without any of the technology we consider essential for such projects today. Let's understand the challenge they faced. Petra sits in the Wadi, a valley in southwestern Jordan that receives less than 6 inches of rain per year. That's classified as hyper-arid, one step away from being classified as a true desert. To put that in perspective, Los Angeles gets 15 inches of rain per year. Phoenix gets 8 inches, Petra gets 6, in some years, less. The nearest reliable water source, the Ain Musa Spring, is 5 miles away across mountainous desert terrain. 5 miles might not sound like much, but understand what those 5 miles entailed. The route crosses deep wadis, those dry riverbeds that can transform from bone-dry gullies to raging torrents in the span of minutes when flash floods strike. It crosses areas where solid rock cliffs drop hundreds of feet. It requires navigating around geological formations that make direct paths impossible. Flash floods in this region aren't gentle rain showers. When storms hit the mountains surrounding Petra, water funnels down through the narrow canyons with tremendous force. Modern measurements have documented flows reaching speeds of 20 miles per hour, carrying boulders the size of cars. The force is enough to strip soil from bedrock, to undercut cliff faces, to destroy anything not built to withstand it. The Nabataeans had to build their water systems to not only survive these floods, but to harness them. The temperature swings from scorching days that can exceed 100 degrees Fahrenheit to freezing nights where temperatures drop below 32 degrees. This daily thermal cycling places enormous stress on any structure. Rocks expand and contract. Seals between pipe sections flex. Over time, this cycling would destroy most building materials. The Nabataeans had to account for this in their designs. The rock itself presented another challenge. Petra's famous rose-coloured sandstone is beautiful, easily carved, and perfect for creating those stunning monuments. But it's also porous. It absorbs water like a sponge. It weeps moisture. Any water system built into this stone had to be sealed carefully, or the precious water would simply disappear into the rock itself. Modern archaeologists have found that some cisterns lose up to 20% of their water through seepage if they're not properly lined. And yet the Nabataeans chose this location to build their capital city, the heart of a trading empire that would flourish for over 700 years. They didn't stumble into this location by accident. They chose it deliberately, fully aware of the water challenge they faced, because what Petra lacked in water, it made up for in strategic value beyond measure. Why here? Because this impossible location was perfect for their purposes. The narrow entrance through the sick made Petra virtually unassailable by armies. The surrounding cliffs provided endless building material. The position placed them at the crossroads of major trade routes connecting Arabia, Egypt, Syria, and the Mediterranean. Caravans carrying frankincense, myrrh, spices, and silk had to pass through Petra. The Nabataeans controlled this choke point and grew wealthy beyond measure, but none of it would have been possible without solving the fundamental problem. Water. A city of 20,000 people needs massive amounts of water, not just for drinking, for cooking, for bathing, for animals, for the gardens and fountains that turn this desert fortress into a showcase of civilization, for the public baths that demonstrated Petra's sophistication to visiting merchants and diplomats, for agriculture in the surrounding terraces. Modern calculations suggest Petra needed to manage hundreds of thousands of gallons of water daily. In a desert, with no nearby source, the challenge wasn't just difficult, it was theoretically impossible. The Nabataeans didn't just solve it, they created a masterpiece. Their solution began with obsessive attention to every drop of water in the environment. They built hundreds of cisterns throughout the city and surrounding areas. Not simple holes in the ground, but carefully engineered reservoirs carved into the bedrock. Some could hold thousands of cubic meters. These cisterns were strategically positioned to catch rainwater when it fell, which wasn't often, but when it did, the Nabataeans were ready. They carved channels in the rock to guide runoff into collection points. They shaped the terrain itself to funnel water where they wanted it to go. But cisterns alone couldn't sustain a city. They needed constant water, year-round, drought or no drought. That's where the spring systems came in, and this is where Nabataean engineering becomes almost impossible to believe. The main water supply system they created is called the Wadi Mataha pipeline. Picture this construction challenge in your mind. 5 miles from Petra, high in the mountains, sits a spring called Ain Musa. Local tradition claims this is the place where Moses struck the rock to bring forth water, though the Nabataean engineers needed no miracles. They needed knowledge, precision, and extraordinary skill. The Nabataeans needed to bring that spring water to their city. Think about what that means. They had to survey a route across 5 miles of some of the most difficult terrain imaginable. They had to calculate gradients without modern surveying equipment. They had to plan for every obstacle along the way, and then they had to build it. Actually, construct it, make it work, make it last. The route crosses multiple wadis. These dry riverbeds present a unique engineering challenge. During most of the year they're empty, just rocky gullies cutting through the landscape. But when rain falls in the mountains, they transform into devastating torrents. Water rushes through with such force it can move massive boulders. Any pipeline crossing a wadi has to survive this destructive force repeatedly, year after year, potentially for centuries. The Nabataean solution was to build elevated platforms across the wadis. Not simple, bridges, carefully engineered structures designed to let floodwaters pass beneath, while keeping the pipeline above the destruction. The platforms had to be high enough that even the worst floods wouldn't reach them, strong enough to withstand earthquakes, which are common in this geologically active region, and precise enough to maintain the exact gradient required for optimal water flow. Then came an even greater challenge. Part of the route runs along the near vertical eastern face of Jebel al-Kubthar mountain. We're talking about cliff faces that rise hundreds of feet above the valley floor. The Nabataeans had to construct a platform on this cliff face. Imagine the engineering required. Every stone placed had to be secured against gravity. Workers had to position themselves on scaffolding hundreds of feet in the air, with nothing but desert floor below them. And they had to do this while maintaining precision, because the platform had to support a pipeline at exactly the right angle. On this platform, they laid tens of thousands of handmade terracotta pipe sections. Each pipe had to be crafted individually by skilled potters. The clay had to be sourced, prepared, shaped on a wheel, and fired in kilns. Each section measured roughly 2 feet in length, meaning they needed thousands upon thousands of pieces for a 5-mile pipeline. Each one had to be uniform in thickness to withstand pressure. Each one had to be perfectly cylindrical to allow smooth water flow. The ends of each pipe section were carefully shaped. One end tapered slightly wider, the other slightly narrower, creating a socket joint when fitted together. This wasn't casual craftsmanship. The taper had to be precise. Too loose and water would leak at the joints. Too tight and the pipes wouldn't fit together properly. The Nabataean potters achieved a standardization that allowed any pipe section to fit any other section. That's quality control that rivals modern manufacturing standards. Once the pipes were made, they had to be transported to the construction site, 5 miles across desert terrain. Thousands of fragile ceramic tubes, each one valuable, each one breakable. The logistics alone are staggering. How many trips did it take? How many workers were involved in just the transport? How did they prevent damage? Then came installation. Each pipe section had to be socketed into the next with perfect alignment. The joints were sealed with a mixture of lime mortar and other materials that archaeologists are still analysing. This sealant had to remain flexible enough to accommodate slight movements from earthquakes and thermal expansion, while being waterproof enough to prevent leaks for centuries. The formula they developed worked spectacularly. Pipe sections excavated after 2,000 years still have intact sealant, but here's where the Nabataean achievement becomes almost impossible to believe. The entire pipeline, over its 5-mile length, maintains a specific, constant angle, not just approximately, not within a reasonable tolerance, exactly 2 degrees of slope, maintained consistently from beginning to end. Think about what that means in practical terms. Over 5 miles, a 2-degree slope means the pipeline drops roughly 900 feet in elevation. That's significant, but the key is that the descent is steady and consistent. No sudden drops, no flat sections, a constant, gradual downward slope of exactly 2 degrees for the entire distance. Maintaining that precision over 5 miles of mountainous terrain requires surveying skill that's hard to comprehend. The Nabataeans didn't have laser levels. They didn't have theodolites. They didn't have GPS. They had A-frames, plumb bobs, water levels, and their eyes. And somehow, with these simple tools, they achieved precision that modern surveyors find remarkable. Why 2 degrees specifically? This is where modern science caught up with ancient practice and discovered something extraordinary. In 2014, researchers at the University of Chicago used computational fluid dynamics software to analyze the Wadi Mataha pipeline design. They created computer models of the pipeline, testing what would happen at different slopes: 1 degree, 2 degrees, 3 degrees, 4 degrees. They ran simulations of water flow through each configuration. The results were startling. At 2 degrees, the pipeline achieves maximum flow rate for its specific diameter and configuration. The water moves fast enough to carry sediment through without depositing it, which prevents blockages. It moves slow enough that it doesn't create destructive turbulence that could damage the pipes. The pressure remains relatively stable throughout the system, minimizing leaks. The flow rate matches almost exactly what modern hydraulic engineering would recommend. Increase the slope to 3 degrees, and flow rate actually decreases because turbulence increases, creating resistance. More importantly, the faster flow creates pressure variations that cause leaks at the joints. Decrease to 1 degree, and the flow is too slow. Sediment begins to settle out. Over time, this sediment would block the pipeline. Water pressure drops below useful levels. 2 degrees is optimal. Not approximately optimal, precisely optimal for the constraints the Nabataeans faced. The mathematics required to calculate this optimal angle involved differential equations and fluid mechanics principles that weren't formalized in Western mathematics until the 18th century. The Nabataeans built this pipeline in the 1st century BCE. How did they know? The only explanation that makes sense is empirical observation, combined with extraordinary skill. They must have built test sections, experimented with different slopes, observed how water behaved at each angle, measured flow rates somehow, noticed where sediment deposited, tracked where leaks developed, and from all these observations, they determined that 2 degrees worked best. This represents scientific methodology in action. Hypothesis, experiment, observation, conclusion. They might not have written papers about it. They might not have developed mathematical models, but they were doing science, real, practical, effective science that produced engineering results matching what our best computer software would recommend 2,000 years later. Let's talk about those pipes themselves in detail, because when you really examine them closely, they reveal layer upon layer of sophistication. In the museum at Petra, they have 2 sections of the original terracotta pipe on display, where visitors can examine them up close. Most tourists walk past with barely a glance, seeing just old clay tubes, but engineers who understand pipe design stop in their tracks. These aren't crude clay tubes shaped by hand and baked in primitive kilns. The walls are uniform in thickness, about 3/4 of an inch throughout. That uniformity is crucial. If one part of the pipe is thinner, that's where it will crack under pressure. The Nabataean potters achieved this uniformity using techniques that show remarkable skill. The interior surface is smooth, almost polished. This isn't merely aesthetic. A smooth interior reduces friction, allowing water to flow more efficiently. Modern pipe manufacturers spend considerable effort achieving smooth interior surfaces because rough surfaces create turbulence that reduces flow rate and can cause erosion. The Nabataeans understood this 2,000 years ago, but it's the ends that truly astound engineers. Each pipe section has a wider bell end and a narrower spigot end. The bell end has a smooth tapered interior that accepts the spigot end of the next pipe. The spigot end tapers on the outside to fit snugly into the bell. When joined, this creates a socket joint that has multiple engineering advantages. First, it prevents leakage far better than just butting 2 straight pipes together would. The overlapping joint creates a longer sealing surface. Even if the sealant degrades slightly, the mechanical fit prevents major leaks. Second, it allows for slight angular flexibility. If the ground shifts, if there's minor earthquake movement, if thermal expansion causes stress, the socket joint can accommodate a small amount of deflection without breaking. This makes the entire pipeline more resilient to the geological and environmental forces in Petra. Third, and this is where it gets really clever, the socket design prevents sediment from accumulating at joints. With butt joints, sediment tends to catch on the lip where pipes meet. Over years, this builds up and can eventually block flow. Socket joints, when properly designed, create a smooth interior profile that doesn't catch sediment. Fourth, the design allows damaged sections to be replaced without dismantling large portions of the pipeline. If a pipe cracks, Workers can excavate just that section, remove it, and socket in a new piece. This maintainability is crucial for a system expected to operate for centuries. Now here's what makes engineers pause when they see these pipes. The tapered socket design that the Nabataeans perfected is the same basic design principle that modern pipe manufacturers use today. It's called a bell and spigot joint, and it's considered standard practice for cast iron, PVC, and ceramic pipes in the modern world. When did we invent this design in the modern era? The late 19th century. Various European and American manufacturers began producing bell and spigot pipes for municipal water systems in the 1880s and 1890s. Around 2,000 years after the Nabataeans were using the exact same principle. The Nabataeans weren't just ahead of their time, they developed a solution so fundamentally sound that when modern engineers faced the same problems, they arrived at the same design independently. That's not luck. That's deep understanding of how pipes, water flow, and joinery work. Recent archaeological analysis has revealed even more sophistication. Some pipe sections show evidence of quality control markings. Small stamps or marks on the exterior that archaeologists believe indicated which potter made that section, which kiln it was fired in, or which batch of clay was used. This suggests an organized production system with accountability built in. If pipes from a particular potter kept failing, they knew who to talk to. The firing process itself required expertise. Clay pipes need to be heated to around 900 degrees Celsius to properly vitrify, making them waterproof and durable. Too cool, and they remain porous and weak. Too hot, and they deform or crack. The Nabataeans had to maintain precise temperature control in their kilns, probably using nothing more sophisticated than experience and observation of the flame color. And they had to produce thousands of these pipes, tens of thousands, all to the same specifications, all with the same quality. The scale of the ceramics industry required to support Petra's water system represents a major sector of the Nabataean economy. Specialized workshops, trained potters, kilns running constantly, quality control systems, distribution networks to get finished pipes to construction sites. Modern archaeologists have found evidence of these workshops in the areas surrounding Petra. Waste heaps containing broken or malformed pipes that didn't meet quality standards. Kiln sites with layers of ash showing decades or centuries of continuous use. Clay sources that show signs of extensive extraction. The Nabataeans built an entire industry to support their water infrastructure. But the Wadi Mataha wasn't their only pipeline. They built multiple systems, each with different engineering solutions based on the specific challenges of that route. The Sick pipeline, the one you can still see when you walk through the gorge, uses a completely different design philosophy. It's built into the rock wall on both sides. The channel on the left is an open trough carved directly into the cliff face, covered with stone slabs to prevent evaporation and contamination. The ceramic pipes on the right are embedded in the wall at road height initially, but as you walk deeper into the Sick, notice something remarkable. The road drops dramatically, but the pipes don't drop at the same rate. The Nabataeans kept them descending slowly, maintaining pressure, so that by the time you reach the city centre, there's significant elevation difference between the pipes and the ground. This creates water pressure, enough pressure to push water upward into fountains and public baths. They understood hydraulic pressure. They engineered it into their design deliberately. The Sick pipeline also demonstrates another brilliant innovation. Instead of pressurized flow, which would cause leaks in ancient ceramic pipes they designed for partial flow, open channel flow at critical rates. This means the water moves fast enough to carry sediment through without depositing it, but not so fast that it causes erosion or pressure spikes. The flow is stable, predictable, maintainable. Modern analysis of the system using computational fluid dynamics reveals that the Nabataean design is nearly optimal for the constraints they faced. Nearly optimal. using 2,000-year-old technology. The third major system, the Ain-Brak pipeline, shows yet another engineering innovation only recently discovered by modern researchers. One branch of this pipeline has an offshoot segment leading to a water collection basin adjacent to the main line. At first, archaeologists didn't understand its purpose. Then hydraulic engineers analysed it with modern software. The basin functions as a surge tank. When flow instabilities occur downstream, when pressure spikes happen due to changes in demand or temporary blockages, the surge tank absorbs the excess pressure. It prevents the system from developing destructive water hammer effects that could crack the pipes. The Nabataeans invented surge tanks, a technology we thought was developed much later. But managing the delivery of water was only half the challenge. They also had to manage flash floods. In the desert, when rain does fall, it doesn't fall gently. It comes in torrents. Entire wadis can go from bone dry to raging rivers in minutes. These flash floods are powerful enough to destroy anything in their path. The Nabataeans needed to protect their city, protect their water systems, and if possible, capture that floodwater for storage. So they built dams, not across the Sikh itself, which would have blocked the main entrance, but in the wadis surrounding Petra. These weren't simple earth mounds. They were carefully engineered structures designed to slow water flow, reduce erosion, and redirect floods into controlled channels. When floods came, the dams shunted water into diversion channels that fed into the cistern network. Instead of destroying the city, the floods filled the reservoirs. Disaster became resource. The main dam they built across the valley entrance is a marvel of engineering in its own right. It had to withstand enormous pressure during floods while allowing normal passage during dry periods. The design includes spillways, overflow channels, and sacrificial sections designed to fail in controlled ways if the flood exceeds design limits. It's defensive engineering, anticipating failure modes and planning for them. Modern engineers who study Petra's flood control systems often express admiration for the sophistication of the approach. The Nabataeans didn't just react to their environment, they shaped it to serve their needs. Inside the city itself, the water distribution network becomes even more complex and reveals the full scope of Nabataean urban planning. Hundreds of underground cisterns dot the urban landscape, and each one represents significant engineering in its own right. These aren't simply holes dug in the ground and lined with stone. They're carefully designed water storage facilities that had to solve multiple problems simultaneously. First, the structural challenge. A cistern holding thousands of cubic meters of water experiences tremendous hydrostatic pressure on its walls. Water is heavy. Each cubic meter weighs 1,000 kilograms, or about 2,200 pounds. A medium-sized cistern holding 50 cubic meters of water has 50 metric tons pushing outward on its walls. The Nabataeans had to design walls strong enough to contain this pressure without collapsing, using nothing but stone and mortar. They solved this through a combination of clever geometry and solid construction. Many cisterns are bell-shaped, wider at the bottom than at the top. This shape naturally resists the outward pressure of the water. It's the same principle used in modern water towers. The shape is structurally efficient, requiring less material to achieve the same strength as a cylindrical cistern would. The walls are constructed of carefully cut and fitted stones, not massive blocks like those used in the monuments, but precisely sized pieces that interlock to distribute loads evenly. The stonework shows incredible craftsmanship. Joints are tight, surfaces are smooth, corners are properly reinforced. This is masonry work that would impress modern stonemasons. But structural integrity was only the beginning. The cisterns also had to be waterproof. Remember, the sandstone of Petra is porous. Leave water sitting against bare rock, and it will soak in like a sponge. The Nabataeans developed a waterproofing system that's still effective 2,000 years later. They plastered the interior walls with a specialized mixture. Analysis of this plaster reveals a sophisticated formula. The base is lime mortar, which is common enough, but the Nabataeans added crushed pottery, volcanic ash, and other materials in specific proportions. This created a hydraulic cement that actually hardens underwater and becomes extremely waterproof. The application technique mattered as much as the formula. The plaster had to be applied in layers, each one allowed to partially cure before the next was added. This created a thick, durable coating with no weak points. The surface was then burnished, compressed using smooth stones to create an almost glass-like finish. This burnishing reduces porosity even further and creates a surface that resists algae growth. Recent studies have found that well-maintained Nabataean cisterns lose less than 2% of their water volume to seepage. 2% in porous sandstone. That's extraordinary waterproofing by any standard. The cisterns were connected to the city's water network through a system of channels that shows equally sophisticated planning. Each cistern had an inlet channel, bringing water in, and often multiple outlet channels for distribution. The inlets were positioned high on the cistern wall, allowing water to enter at the top and flow downward. This serves multiple purposes. First, it aerates the water. As water tumbles down into the cistern, it absorbs oxygen, which keeps it fresher and prevents anaerobic bacteria from thriving. Second, it creates circulation patterns that prevent stagnation. Fresh water coming in at the top mixes with stored water, preventing the formation of distinct layers that could lead to water quality problems. The outlets were positioned at different heights. The highest outlets were used when the cistern was full, drawing water from near the top, where it was freshest. Lower outlets could be used as water levels dropped, but they never placed an outlet at the very bottom. The lowest portion of the cistern was left as dead storage. This had a practical purpose. Any sediment that got past the filtration systems would settle to the bottom, where it wouldn't contaminate the water being drawn out for use. This brings us to the filtration systems, which represent perhaps the most impressive aspect of Nabataean water engineering. They understood that clean water was crucial for public health, and they built purification into their infrastructure from the beginning. Before water entered the main cisterns, it passed through settling basins. These are separate, smaller chambers, where water flow is deliberately slowed. When water slows down, suspended particles settle out due to gravity. Larger particles settle first. Smaller particles take longer, but eventually settle too. The Nabataeans built multiple settling basins in sequence, each one removing progressively finer particles. The design of these settling basins shows real understanding of fluid dynamics. The entrance channel brings water in at one end. The exit channel draws water from the opposite end, near the top. This forces water to flow the entire length of the basin, maximizing the time available for settling. The bottom is shaped to collect sediment in specific areas where it can be periodically removed without disturbing the entire basin. Some settling basins included baffle walls. These are internal walls that don't reach the full height of the basin. Water has to flow under or around them, creating a serpentine path. This increases the effective length of the basin without increasing its physical size, further slowing the water and improving settling efficiency. The Nabataeans also use biological filtration, though they might not have understood it in those terms. Some channels bringing water into the city were left open to sunlight. Algae and beneficial bacteria would grow on the stone surfaces. As water flowed over these biological films, the microorganisms removed nutrients and consumed harmful bacteria. Modern water treatment plants use similar biofilms deliberately. The Nabataeans observed that water flowing through sun-exposed channels arrived cleaner than water flowing through covered channels, and built that observation into their system design. For particularly important water sources, such as those feeding the royal palace or major public buildings, they added additional filtration stages. Some cisterns have been found with carefully graded layers of gravel, sand, and crushed charcoal at the bottom. Water percolating through these layers underwent mechanical and chemical filtration. The gravel removed larger particles, the sand removed finer sediment, the charcoal adsorbed dissolved impurities and removed odours. This is essentially the same principle used in modern slow sand filters. The layers have to be maintained in the correct order and periodically cleaned or replaced. The fact that the Nabataeans included such filtration systems suggests they understood water quality at a level that wouldn't be matched in Europe until centuries later. Each cistern was connected to channels that fed them during rain or from the pipeline systems, but the connections weren't simple pipes. They included control structures, sluice gates that could be opened or closed to direct water flow, overflow channels that would activate when a cistern filled, directing excess water to the next cistern in the network, rather than allowing it to spill wastefully. Some cisterns were private, serving individual, wealthy households. These tended to be smaller, but were often more elaborately decorated with carved stone surrounds and decorative elements. Others were public, accessible to everyone. The largest public cisterns could hold enough water to supply hundreds of people for weeks. The placement of cisterns throughout the city shows careful urban planning. Every neighbourhood had access to clean water within a reasonable walking distance. Major public spaces, like the market areas and the ceremonial centre, had particularly large cisterns nearby. The positioning also shows awareness of topography. Cisterns were placed at various elevations, allowing gravity to move water downhill to where it was needed. Recent excavations have revealed even more sophistication. Some cisterns have double wall construction. An inner waterproof shell holds the water. An outer structural shell provides strength. Between them is an air gap, sometimes as much as 6 inches wide. This air gap provides insulation, keeping water cool in the brutal summer heat and preventing freezing in winter when temperatures drop below freezing. It's the exact same principle used in modern thermos bottles. The air gap prevents heat transfer. Water in these insulated cisterns could remain 20 degrees Celsius cooler than the surrounding air temperature. That meant the difference between water that was barely drinkable in summer heat and water that was refreshingly cool. The Nabataeans even built in overflow and emergency drainage systems for the cisterns. If a cistern overfilled, excess water was directed into channels that carried it away from the city, rather than letting it flood the streets. If a cistern needed to be emptied for cleaning, which had to happen periodically, there were drainage channels that could be opened to empty it quickly. Let's talk about the scale of the operation required to build all this. The Wadi Mataha pipeline alone consists of tens of thousands of individual pipe sections. Each one had to be shaped by hand from clay, fired in kilns, transported to the construction site, and installed with perfect alignment. The elevated platform supporting it required massive amounts of stone cutting and placement. The surveying required to maintain that precise 2-degree angle over 5 miles demanded teams of skilled workers taking measurements, adjusting elevation, rechecking constantly. The entire system, all the pipelines, all the cisterns, all the dams, all the channels, represents millions of man-hours of skilled labour. The project management alone is staggering to contemplate. Coordinating that many workers, that many specialised crafts, that much material transport in the desert, while keeping the city functioning. And they didn't just build it once, they maintained it for centuries. Repaired damage from earthquakes, adapted to changing needs as the city grew, upgraded sections when better designs were developed. The water system of Petra wasn't a static achievement. It was a living, evolving infrastructure that kept pace with one of the ancient world's most important cities. The result was nothing short of miraculous. In the heart of one of Earth's harshest deserts, the Nabataeans created an oasis. Visitors to Petra during its height described streets lined with gardens, public fountains flowing constantly, elaborate bathhouses rivaling those in Rome, pools and water features decorating the monuments, the sound of running water echoing through the canyons, all of it made possible by engineering genius. Think about what this achievement meant. Every major civilization in history has been built around water. Egypt had the Nile, Mesopotamia had the Tigris and Euphrates, Rome had the Tiber, China had the Yellow River, but Petra had nothing, just desert. The Nabataeans looked at that impossible situation and said, "We'll bring the water to us." And they did it so well that their city thrived for 7 centuries. The sophistication of their water management gave them tremendous advantages. During sieges, when enemies expected Petra's water supply to run out, the defenders had massive reserves in their cisterns and continuous flow from protected pipelines. The city could outlast any besieging army. During droughts that devastated surrounding regions, Petra's water system kept functioning. The reliability of their supply made them invaluable as a trade centre. Caravans knew they could always find water in Petra. That reliability translated directly into economic power. But perhaps the most impressive aspect isn't the technical achievement, though that's remarkable enough. It's the knowledge that achievement required. The Nabataeans clearly understood principles of hydraulic engineering that Western civilization wouldn't formally develop for centuries. They knew about optimal flow rates and pressure management. They understood sedimentation and filtration. They grasped concepts of material science, knowing which clays would produce the best pipes, which mixtures would create waterproof seals, which stone would resist erosion. Where did this knowledge come from? The Nabataeans were traders, and Petra sat at the crossroads of the ancient world. They had contact with Egyptian, Greek, Roman, Persian, and Arabian civilizations. They borrowed ideas, adapted technologies, integrated knowledge from multiple sources, but they didn't just copy. They innovated. The specific solutions they developed for Petra's unique challenges show original thinking, creative problem solving, and willingness to experiment. Recent research has revealed that the Nabataeans also borrowed from their own past. Archaeological evidence suggests they built and maintained oases along their trade routes throughout Arabia. Each oasis required water management in desert conditions. Each was a laboratory where they could test ideas, refine techniques, learn what worked. By the time they built Petra, they had centuries of accumulated knowledge about desert water systems. They also learned from failure. Early sections of some pipelines show design features that were later abandoned or modified. Cisterns from Petra's earliest days are simpler than later ones. The system evolved over generations, each improvement building on the lessons learned from what came before. This is the hallmark of true engineering, not getting it perfect immediately, but developing systems that work, learning from them, and continuously improving. Now let's jump forward 2,000 years because the story of Petra's water system isn't over. In August 2024, an archaeological team led by Dr. Piers Paul Kriesman made a discovery that captured global attention. Using ground-penetrating radar, they detected a hidden chamber beneath the Treasury, that iconic structure everyone recognizes from Indiana Jones. When they excavated, they found something archaeologists almost never find in Petra: 12 complete human skeletons, surrounded by grave goods made of bronze, iron, and ceramic. The tomb was intact, undisturbed for 2,000 years. Among the artifacts, one skeleton was found holding a ceramic vessel, its shape remarkably similar to the Holy Grail from the Indiana Jones movie. The coincidence was so striking that Josh Gates, the television host documenting the discovery, called it an awesome moment of history imitating art. But the real significance goes far beyond Hollywood parallels. This tomb provides insight into Nabataean burial practices that archaeologists have desperately sought. Most tombs in Petra have been found empty or disturbed long ago. This one, hidden beneath the most famous structure in the city, was perfectly preserved. The architecture of the tomb itself is unique. The construction techniques differ from other known Nabataean tombs. The placement, directly beneath the Treasury at the main entrance to the city, suggests these were people of enormous importance. The discovery raises tantalizing questions. Who were they? Why were they buried in such a prestigious location? What can their remains tell us about Nabataean life, health, diet, even genetics? Analysis of the skeletons is ongoing, but preliminary findings are already fascinating. The bone structure suggests these weren't people who suffered from malnutrition or chronic disease. They lived well, at least for the standards of their time. The artifacts found with them show sophisticated metallurgy and ceramic work. The discovery also highlights how much we still don't know about Petra. Despite 2 centuries of our archaeological investigation, despite modern technology like ground-penetrating radar and LiDAR, the city continues revealing secrets. The Treasury itself remains mysterious. When was it built? By whom specifically? For what exact purpose? The traditional theory says it's a mausoleum, but until this recent discovery, no skeletal remains had ever been found associated with it. And here's something that gives archaeologists hope. Much of Petra remains unexcavated. The visible monuments, the structures tourists see, represent perhaps 15% of the total city. The rest lies buried under centuries of sand and debris, or it's carved into cliffs in areas too remote or dangerous to safely explore. Every year, new discoveries emerge. In 2016, satellite imagery revealed a massive ceremonial platform nobody knew existed. Recent excavations have uncovered residential areas, workshops, more sophisticated water management features. The complete picture of Nabataean Petra is still being assembled, piece by piece, discovery by discovery. But let's return to the water system, because that's where Petra's true marvel lies. Modern engineers studying the system often express a mix of admiration and frustration. Admiration for the sophistication and effectiveness of the design. Frustration because in many ways, the Nabataean solutions are better than modern approaches would be. Consider this: if you tasked a modern engineering firm with bringing water from a spring 5 miles away across mountainous desert terrain to supply a city, they would use powered pumps, electric or diesel. They'd install pressure vessels and automated controls. They'd use PVC or steel pipes. The system would work beautifully, until the power failed, or the pumps broke down, or the sophisticated controls malfunctioned, or political instability disrupted fuel supplies. The Nabataean system used gravity, only gravity, no pumps, no power, no complex machinery. It worked for 7 centuries continuously. It worked through earthquakes and floods and wars and changes of government. It required minimal maintenance. A crack in a pipe, replace that section. Sediment build up in a channel, clean it out. The system was robust, resilient, and sustainable in ways modern systems often aren't. There's a concept in engineering called appropriate technology. It means designing solutions that match the context where they'll be used. High tech isn't always better if it creates dependencies and failure points. The Nabataeans understood this intuitively. They built systems that their society could actually maintain and operate long term. That's wisdom we sometimes forget in our rush to apply the latest technology to every problem. Modern researchers studying Petra's water system have published papers with titles like "Ancient Engineering Predates Modern Science by 20 Centuries." They're not exaggerating. Computational fluid dynamics analysis of the pipeline designs consistently shows that the Nabataeans achieved results that match or exceed what modern software would recommend. They did it through empirical observation, experimentation, and accumulated knowledge passed down through generations. This raises profound questions about the narrative we tell about technological progress. We like to think of it as linear. Ancient civilizations were primitive. Then gradually we got smarter. Then the scientific revolution happened, and now we're advanced. But Petra shows that ancient peoples were capable of sophisticated engineering that rivals modern work. They had different tools, different knowledge bases, different constraints, but they weren't less intelligent. They weren't less capable of solving complex problems. In some ways, they might have been more impressive, because they achieved extraordinary results with minimal tools. They had to be smarter, more observant, more creative to overcome the limitations of their technology. The Nabataean engineer, who figured out that 2-degree slope for the Wadi Mataha pipeline, didn't have computer models to test options. He had to understand water behavior through direct observation and reasoning. That requires a depth of understanding that using simulation software doesn't necessarily provide. There's also something beautiful about the integration of the water system with the city itself. The Nabataeans didn't hide their engineering. The channels in the Sick are visible. The cisterns dot the landscape. Water features became architectural elements. The sound of flowing water would have been omnipresent in Petra, a constant reminder of the triumph over the desert. Engineering wasn't separate from culture. It was part of the city's identity. Compare that to modern cities, where infrastructure is deliberately hidden. Water comes from pipes buried underground. Sewage leaves through systems we never see. Power lines are preferably buried. We've made our engineering invisible, which perhaps disconnects us from understanding and appreciating it. The Nabataeans celebrated their water system. It was a source of pride, a demonstration of capability, proof of their civilization's sophistication. Today, remnants of the system still function. Some of the cisterns still fill when it rains. Some of the channels still guide water along the paths carved 2,000 years ago. The terracotta pipes, when archaeologists find them in place, are often still sound. The waterproof plaster in the cisterns after 2 millennia still prevents leakage. This is engineering built to last, and it has. But time and nature have taken their toll. Earthquakes have damaged sections. Erosion has worn away others. Modern development and tourism have inadvertently impacted some areas. There's an irony that Petra's greatest enemy today might be its own success as a tourist destination. Hundreds of thousands of visitors per year put stress on the ancient structures. Well-meaning but poorly executed restoration efforts have sometimes caused more harm than good. Preserving Petra for future generations requires balancing access with conservation. It requires understanding the original engineering well enough to maintain it properly. It requires resources and expertise. Jordan has made tremendous efforts, and Petra is a UNESCO World Heritage Site with international support. But the challenges are real and ongoing. For anyone studying ancient engineering, Petra offers endless lessons about problem-solving under constraints, about sustainable design, about the value of empirical observation, about building systems that can be maintained by the people who use them, about integrating infrastructure with culture, about human capability when necessity drives innovation. But perhaps the deepest lesson is about perspective. When we look at ancient ruins, it's easy to see them as primitive, as less than what we have now. Petra shatters that illusion. The Nabataeans built something extraordinary, something that worked magnificently for centuries, something that still impresses the world's best engineers. When they study it closely, they took an impossible situation and made it possible. They built a city in a place where there should be no city. They created abundance in scarcity. They turned the harshest desert into a garden. Not through magic, not through divine intervention, through knowledge, skill, determination, and brilliant engineering. This is what humans can accomplish when we refuse to accept limitations as final. When we observe carefully, think creatively, and build thoughtfully. When we learn from our mistakes and improve over generations. When we apply intelligence and persistence to seemingly impossible challenges. The water system of Petra stands as one of humanity's great achievements, not because it used advanced technology by our standards, but because it solved an incredibly difficult problem with elegance and effectiveness, because it demonstrates that ancient peoples were capable of sophisticated engineering that we're still studying and learning from today. Every time archaeologists make a new discovery at Petra, every time researchers analyze another aspect of the water system, they find more to admire, more sophistication they hadn't previously recognized, more evidence of knowledge they didn't realize the Nabataeans possessed. The mystery isn't really how they built it. With enough time, dedication, and skilled craftspeople, the physical construction becomes understandable. The mystery is how they knew what to build. How did they develop the understanding of hydraulic principles that made their designs so effective? How did they achieve such precision without modern surveying tools? How did they predict that their systems would work before they built them? Some of that knowledge came from other civilizations. Some came from experience with earlier, smaller projects. Some came from experimentation and learning from failure. But some of it seems to have come from a depth of understanding about how water behaves that we can only admire in hindsight. As we face our own challenges with water management in the 21st century, with climate change affecting water availability, with growing populations straining resources, with the need for sustainable solutions, perhaps we should look back at Petra, not to copy their specific techniques, which were designed for their specific context, but to learn from their approach. Design for sustainability. Build systems that can be maintained. Use local resources cleverly. Observe natural processes carefully. Plan for the long term. The Nabataeans didn't just solve their water problem. They created a system that supported their civilization for 700 years. 7 centuries of continuous operation with minimal technological advancement. Because they built it right the first time, or more accurately, they built it thoughtfully, learned from it, and improved it continuously until they had something that worked. That's the kind of thinking we need today. Not just solving immediate problems, but creating solutions that will still work generations from now. Not just using the most advanced technology available, but using the most appropriate technology for the context. Not just engineering for efficiency, but engineering for resilience. Petra teaches us that ancient peoples were our equals in intelligence and capability. They faced different challenges with different resources, but they met those challenges with remarkable sophistication. The water system they built rivals anything modern engineers might design for similar circumstances. In fact, modern engineers studying Petra often conclude that the Nabataean approach might actually be superior to what we do today, because it's more sustainable, more resilient, and more maintainable over the very long term. This is the wonder of Petra, not just that it's beautiful, though it absolutely is, not just that it's ancient, though it certainly is, but that it represents human achievement at the highest level, the triumph of knowledge over ignorance, the victory of determination over limitation, the power of careful observation and thoughtful design to solve problems that seem impossible. Every drop of water that flowed through Petra's pipelines represented a victory over the desert. Every fountain that played in the city's squares was a declaration that humans could thrive anywhere with enough intelligence and effort. Every cistern that filled with rain was a testament to planning and preparation. The whole system, in its intricate complexity and elegant simplicity, showed what we're capable of accomplishing. And the story continues. New discoveries at Petra happen regularly. The 2024 tomb beneath the Treasury is just the latest. More secrets remain buried. More engineering marvels wait to be understood. Each discovery adds to our appreciation of what the Nabataeans achieved. So the next time you see a picture of Petra, the next time the Treasury appears in a movie or documentary, remember what you now know. Behind that beautiful carved facade, beneath those rose-coloured cliffs, throughout that ancient city, runs one of the most sophisticated water systems ever built. a system designed with such skill that modern engineers still study it in awe. A system that brought life to the desert and sustained a civilization for centuries. The Nabataeans looked at an impossible challenge and said, "Watch this." And then they built something that still inspires wonder 2,000 years later. That's the true mystery of Petra. Not how they did it, though that's impressive enough, but that they saw what seemed impossible and made it real through knowledge, skill, and sheer determination. That's human achievement at its finest. That's engineering as art and science combined. That's what happens when we refuse to accept that something can't be done and instead figure out how to make it work. Petra stands in the desert still. The Treasury still catches. The light, the cisterns still fill when rain falls. The channels still guide water along paths carved 2 millennia ago. And we stand in awe, recognizing that the ancient world was capable of wonders that challenge our assumptions about progress and capability. Thank you for joining me on this journey to Petra. Tomorrow, we'll explore another incredible achievement from history's pages. Until then, remember that the greatest mysteries aren't about what was lost. They're about what was accomplished and how we're still learning from it today. If you enjoyed this deep dive, please like and subscribe, and I'll see you in the next episode of Soft Spoken Mysteries.